So we've previously talked about differential rate laws. Now we want to talk about integrated rate laws. All right, in the previous videos, when we talked about rate laws, what we were really talking about were differential rate laws, although almost everybody just calls differential rate laws rate laws. Now, differential rate laws tell us how the rate depends on the concentration. What we're going to look at now are integrated rate laws. And everybody calls these integrated rate laws. So when we just say rate laws, we mean the differential rate laws. If we mean integrated rate laws, we always say integrated rate laws. And integrated rate laws tell us how concentration depends on time. And so we're going to start our discussion by just considering a simple reaction where A is converted into products. And so the differential rate law for that reaction would be rate is equal to K times the reactant raised to whatever its order is. Now, for integrated rate laws, the form that they take depends on the order of the reaction. And so we're going to consider zeroth order, where n is 0, first order, where n is 1, and second order, where n is 2. For each of these different orders, the integrated rate law has a different form. And so here's what the concentration profiles look like for different orders of reaction. Right? So for each of these curves, we're plotting the concentration of the reactant on the y-axis and time on the x-axis. And you can see how the concentration profiles differ for the different orders of reaction. So a zeroth order reaction actually forms just a straight line when we plot the concentration versus time. And first order and second order reactions are not straight lines, they're curved. So for zeroth order reactions, when n is equal to 0, the rate doesn't actually depend on the concentration. We calculate the slope of this line, doesn't matter where we are, the slope is going to be the same. For the first order and the second order reactions, the rate does depend on the concentration. Alright, so what we're going to look at over the next couple slides is what form does the integrated rate law take for the different orders of reaction. And so we're going to start with a first order reaction. So if our reaction is of the form that rate is equal to K times A to the first power, right, the differential rate law tells us how does the rate depend on the concentration. The integrated rate law for a first order reaction is given here. And so it tells us how the concentration depends on time, or in this case more specifically, the natural log of the concentration depends on time. Now, we could write the first order integrated rate law in a number of different forms, but this is one of the most common ways you'll see people write it. The reason we write it this way is because we've essentially written it in the form of the equation for a straight line, right, where we have y is equal to mx plus b. And so if we were to plot on the y-axis the natural log of the concentration, and on the x-axis we plot the time, then what that means is when we make that plot, the slope of that line will be equal to the negative of the rate constant. And the y-intercept will be equal to the natural log of the initial concentration. And so the reason we like to write it like this is because if we monitor the concentration as a function of time, then we can make this plot, use Excel or some other program to fit it to a straight line, and then the slope of that line will tell us the rate constant. And then what we have over here is just another way to write the first order integrated rate law. Okay, if we have a second order reaction, in which case the rate law, or the differential rate law, would be given here, right? Rate is equal to k times a to the second power, so it's second order. This is the form that the integrated rate law would take for a second order reaction. And again, we've chosen to write this in the form of y is equal to mx plus b. And so now if we plot the inverse of the concentration on the y-axis, and again plot time on the x-axis, and we make that plot, then now the slope is going to be just equal to the rate constant, not the negative of the rate constant, and the y-intercept will be 1 over the initial concentration. And so then if we have a second order reaction, we can make this plot, find the slope of the line, and that will tell us the rate constant. All right, and then here we have a zeroth order reaction. So the differential rate law is rate is equal to k times a to the 0 power. Of course, a to the 0 power is just 1, so the zeroth order integrated rate law is just rate is equal to the rate constant. The form that the form that the integrated rate law takes for a zeroth order reaction is given here. And again, we've done y is equal to mx plus b. So if we have a zeroth order reaction, then what we'd want to plot on the y-axis is just the concentration itself. X will be the time, and so now the slope will be minus k, and the y-intercept will be just the initial concentration. So another important topic that comes up when we talk about integrated rate laws is the idea of a half-life. And so the half-life of a reaction is the time required for the concentration of a reactant to fall to 1/2 of its initial value. And so it's a measure of how fast the reaction takes place. Things that have shorter half-lives are faster reactions. Things that have longer half-lives are slower reactions. Now, my initial plan was to derive the expression for the half-life of a first-order reaction. If we do this in class, I think I will do that, but in order of not making this video too long, I think I'm going to skip that. And so instead, I'll just give you the expression. So the half-life of a first-order reaction is equal to 0.693 over the rate constant. Now, just a note on the notation that we're using here. The symbol we use to represent the half-life is T with a subscript 1/2. Right? Don't think of this 1/2 as being a number. It's just a label, right? The whole thing, T 1/2 is the half-life. Don't think about trying to use this 1/2 in anything. It's just part of the label that we use to represent the half-life. Okay, and then I've given you here the expressions for the half-life of a second-order reaction and a zeroth-order reaction. Let me go ahead and write the expression for a first-order reaction again. So one important distinction between the half-lives of first-order, second-order, and zeroth-order reactions is that for second-order and zeroth-order reactions, the half-life depends on the initial concentration. So in some sense, the half-life isn't a constant. We have to factor in how much of the initial material that we're starting with. For a first-order reaction, however, you notice A0 does not appear in that expression. So at least in my experience, we use the half-life concept much more frequently for first-order reactions because the half-life is a constant, and I think we see it less often for second-order and zeroth-order reactions, although you should still be able to use these expressions to calculate the half-life. And just a note on these equations, I'll never ask you to memorize equations. And so the equations for the integrated rate laws or the expressions for the half-lives, I will give those to you. Now, you have to know which one is which, but I'll usually group them together in a way that kind of makes sense when I give you the equation sheet. All right, so I'm going to kind of work through an example sort of partially here, and then I'll do a similar example in one of the later videos where I actually show you how I'm doing the calculations and making the plots that I'm going to show you in this video. So a way that we can use integrated rate laws is to not only tell us what how the concentration depends on time, but we can also determine the order of the reaction using the integrated rate laws, as well as the rate constant. And we can do that using graphs. Right, and we already talked about the fact that if we plot the natural log of the concentration versus time for a first order reaction, we should get a straight line. If we plot 1 over the concentration versus time for a second order reaction, we would get a straight line. And for a 0th order reaction, we would get a straight line if we plot the concentration unchanged versus time. And so for this reaction, the way this problem is set up, we don't know what the order of the reaction is, but we've collected data on how the concentration of the reactant depends on time. So what we want to do in this case, if we want to know the order, we want to make 3 plots, right? So we want to plot the concentration versus time to see if it's a 0th order reaction. We want to plot the natural log of the concentration versus time to see if it's a first order reaction. And then we want to plot 1 over the concentration versus time to see if it's second order. And so we're going to make 3 plots, fit all of those to a straight line, and the one that gives us the best agreement, or right away we evaluate these linear regressions, is by looking at the r-squared value. So the one that gives us the r-squared value closest to 1, that should tell us what the order of the reaction is. Right, and so on the next 3 slides, I'm showing you the graphs that I made. And so I took the data table that we had on the previous slide, and in this one I plotted just the concentration on the y-axis and time on the x-axis. Right, so I'm doing a test to see if this reaction is 0th order. Here's the 0th order integrated rate law. Right, and you can see the concentration is not great. Right, this is the line of best fit. Just looking at it by the eye, it doesn't appear to be very good, and the r-squared value not very close to 1. So probably not a 0th order reaction. Here, now I've plotted the natural log of the concentration on the y-axis and then time on the x-axis. And here things are looking a little bit better, and the r-squared value has improved, but just by looking at it, I think we can see the agreement is still not great. So if I had to choose between 0th order and first order, I'd probably choose first order, but let's see what the second order plot looks like. So now I've plotted the inverse of the concentration, or 1 over the concentration on the y-axis, time on the x-axis. And now, I think we can see just with our eyes that obviously the fit is much better. The r-squared value is improved as well. And so I think we would conclude, based on the agreement of this plot compared to the other two, that this reaction is in fact second order. Alright, so I have 2 more videos on integrated rate laws that are example problems. One of them kind of goes through how you would make these plots in more detail, and then another one is sort of typical of how we might ask other questions related to integrated rate laws.